Hello, everyone. My name is Orlando Moreno, and I'm a performance engineer in the Expand team over here at MariaDB. And today I'm going to be talking about automating database benchmarking with Xbench. So for today's agenda, I'm going to be going over some background information and then talking about the functionality, workflow, and components of Xbench. I'll showcase a quick demo of using the tool and then talk about the current capabilities. Then I'll talk about some real-world usage of Xbench, and then we'll close things off and have a Q&A session after this presentation. But feel free to submit your questions during the presentation. So as some of you may know, benchmarking can be a very tedious task. There's a lot of parameters and variables that you need to take into consideration. And when you multiply out the number of clouds, databases, their configurations, as well as even the benchmarks you want to use, it becomes too many to manually execute for an entire team, let alone a single person. So having some form of automation is crucial for efficiency as well as reproducibility of results. Well, fortunately, we have Xbench, which is a command line tool that automates this complete end-to-end workflow of benchmarking a database in the cloud. It really is as simple as choosing your database, running your workload, and then reporting the results, and has provided us with a streamlined process to help us go from defining requirements all the way to providing performance reports. Now, because it's a command line tool, it can be implemented in your own form of automation. For example, in scripting, as seen here, you can insert it into some nested loops, maybe iterating over different variables such as different databases you like to use or what clouds you like to be in. And Xbench is able to run and automate that entire process. The full process can be completed in less than an hour, depending on your requirements, of course. So where we see Xbench benefit the most is in scenarios that require quick turnaround times. For example, release to release testing. And as you can see here, we've implemented Xbench into a Slack application, which allows us to run benchmarks automatically on builds as they're released, and then printing out the status of whether there's a success or failure. Another example is, let's say you want to reproduce a customer performance issue, or maybe even test out some new features. Because Xbench supports multiple databases, you can also use it to test out other database products and do some competitive analysis. This is just a reminder, though, that this is mainly for testing and for high churn environments, so it's not really for production deployments. So again, the functionality of Xbench is all implemented in Python 3. So there's no additional tooling needed like Kubernetes or Terraform. And the workflow can be controlled through the command line tool, which I'll go into more details in the next slide. I should mention, though, that the provisioning step of this workflow supports multiple cloud environments. And then again, it's implemented in Python. So you just need to know the API if you want to possibly extend Xbench. You can also manage the cluster or instances you create with Xbench as listed here. You can SSH, send and receive files, and do other cluster management functions. We also have a basic security features like whitelisting IPs, so your users can connect to instances implemented in Xbench. And then lastly, the observability of the environment is enabled through the creation and administration of what we call a metric server, which I'll go into more details later. But basically, it allows us to use exporters to collect metrics and create snapshots when we run tests. Now, a typical workflow begins at a request for a benchmark or for some performance data. We use this to collect our requirements and figure out what the goals are. And then we begin defining the certain parameters like what cloud we're using, topology, the implementation, database configuration, and workload. Then we can run Xbench in 3 different phases. The first phase is the provisioning phase, where we provision all of our resources in the cloud and install all the necessary software. The next step is the workload phase, and that's where we create our database, load it with some data, and then run our benchmark suites. This could be an iterative process where we run benchmarks, maybe do some data analysis or start reporting some of that data. And again, it can be a cycle and go through this entire phase over in as many times as you'd like. And then the last phase is the deprovisioning phase, which is basically cleaning up all the resources in the cloud, releasing everything. And this entire workflow can be automated with a single command, which is the run command, but you can also run each step individually as well. Now I'd like to go over some glossary of terms here, basically describing the components of Xbench. So there's three different types of machines to look at, and that's the driver, proxy, and backend. The driver is typically the machine that runs your benchmark, and the backend is where the database runs. The proxy usually is going to be running your supported proxy between the driver and the backend. For example, MaxScale to load balance between the driver and your database. Now, all of these components are laid out in what we call a topology, which is a logical mapping of how all these components are connected to each other. Now, these components can also be located in different clouds or what we call environments. And Xbench is able to encapsulate all of this into a single cluster, so it can manage components from different environments and consider it a single cluster and manage it all in one. And we define all of these components using YAML files, which I'll show in the demo. Okay, so for this demo, I'll be running Xbench from the command line. As you can see, it's as simple as running a Python command with some arguments. So I'll run xb.py with the run command and specify an implementation, topology, benchmark, and workload. I'll go into more details on what these mean in a second here. So let's kick this off and automate the entire workflow. As you can see, this will begin creating a cluster and go through the entire workflow as discussed in the presentation. While this runs, I'd like to go over how we define our parameters. The first piece is declaring what cloud we are using and filling in some details about the infrastructure. In this example, we're using AWS, and we define things like the region, keys, and groups. There is a section for our monitoring service, which I'll show later in the demo, as well as an FTP server in case we'd like to back up and restore. We can define different zones in AWS and also use multiple operating systems given we have access to the AMIs. The next piece is to define our topology, which again is a logical mapping of the components in the cluster. In this example, we're using a simple setup where we have a driver that connects to a backend. In a more complex configuration, where there are multiple components, we can map them out here in this section. So for a distributed database like Expand, for example, we can set up backends in multiple zones and then have different drivers connecting to different proxies that load balance across those backends. Now we must define how each component is implemented. Here we can see that we have a driver and a backend in the AWS cloud. We can define parameters such as the zone, instance type, operating system, and details like network and storage. For this demo, the driver will be running Xbench, and the backend will run MariaDB community server. The instance type for the backend will use a local SSD that's attached, and you can see is defined in the stores section. This next part is where we define the configuration details for MariaDB server. We can specify things like the release number, the data directories, what ports to use, connection parameters, and even override global variables here at the bottom. And lastly, we have our parameters for the benchmark we'll be running. We'll use Xbench and define a couple of parameters which will be used as defaults for any workload we run. Under the workload section, we see that there's only one workload defined named OW demo. And here we have a couple of Xbench specific parameters defined. And if you're familiar with them, you can probably tell that it's an OLTP 90% read, 10% write workload. For the sake of this demo, the size of the database will be small and the runtime will be pretty short. Note that the number of threads here are defined as an array of values. This means that Xbench can iterate over these and test at each level of concurrency. Now let's check back on our Xbench run. It looks like it's provisioned all the resources and is actually starting the sysbench test. Scrolling back up in the log, we can see that the cluster is mapped out first here in this topology graph, and then all of the resources begin to be provisioned in AWS. Afterwards, MariaDB is set up, and we decided to print out some MariaDB parameters that we use. And then it uses Sysbench to load the data and run various tests. So while this is running, I'd like to show you the monitoring service by going to the Grafana dashboard. Here we can see the Grafana dashboard for node exporter. When a cluster is created, some exporters are installed, and then they're run on the instances so that our Prometheus server can scrape the metrics from them. This allows us to view different stats from our cluster live and even create snapshots of completed tests. Since these runs are pretty short, it's going to be difficult to catch the metrics live. So let's look at a snapshot that was created from a test that was run before the demo. In this setup, I ran the same sysbench test, but this time against an expand cluster and for a longer period of time. We have this nice dashboard which shows throughput of the cluster, and we can see how the cluster resources are utilized as the number of threads increase. These kinds of views are saved as Grafana snapshots so that we can reference them later. As the Xbench project develops, we hope to add more exporters and dashboards to improve our observability of the clusters we provision and test. So let's go back to the current run. And it looks like all the tests have finished. We get a nice printout of a table that summarizes the data. And it looks like everything has finished in the deprovisioning phase and has created a Jupyter notebook. So this is the last thing I'd like to look at, is the report that Xbench creates automatically. So the report function creates a Jupyter notebook with the test results summarized and graphed. This can be configured using templates, but for this demo, we see that the chart is pretty basic and contains these 4 data points that we collected. Since we only ran one type of workload, this is going to be the only data that's shown. But with more permutations, the report can be used to graph various test runs. Okay, so that was the end of the demo. Now I'd like to talk about the current capabilities of Xbench. As you can see, we support multiple clouds as well as cloud database services. Most of the databases we support are MariaDB products, but we do support a lot of the other popular databases and even some offered by Amazon and Google. And while we only have 3 benchmarks listed here, it should be noted that each one supports multiple workloads. For example, Benchbase is actually more of like a framework that actually supports different benchmarks and specifications like TPCC and TPCH. So there's a lot of different workloads we can run just from these alone. And then lastly, like I showed in the demo, the Prometheus Grafana combination is really powerful and supports a wide range of exporters. With the combination of node exporter, even some default MySQL exporters, and in-house exporters that we have, it covers a lot of the metrics we need when we're looking at these instances. Okay, so let's switch gears and talk about some real-world usage of Xbench. So in the first example, we're showcasing the ability to run scalability tests. Now, what that means is in most performance benchmarks, you want to scale along multiple vectors, whether it be number of nodes or CPUs or maybe instance types or any other kinds of variables. And in this example, we're testing Expand, which is a distributed database, and we're changing the number of nodes, increasing it from 6 to 9 to 18. As you can see, we run the same Sysbench 9010 workload, and observe the throughput and latency as we increase the number of concurrent threads. So this shows us that Xbench does scale pretty well with this OLTP-like workload, but looking at it from an Xbench perspective, it shows that we can also automate this entire test suite. We can use overrides from the command line, as seen in this example here, by just specifying the backend.count, which is our number of nodes that we use for the backend, which is expand. And just by changing this, we can change the number of nodes used, provisioned, test, and then iterate over those different values that we have. So this shows that we can use Xbench to automate this entire test flow, and we can even create experiments that iterate over multiple variables if we need to. So in this example, we're actually testing different cloud database services, Cockroach Cloud as well as SkySQL Expand. Again, we're looking for an inflection point in the throughput latency curve where the system starts reaching its useful capacity. In the case of Cockroach, it starts to become CPU bound after about 128 threads. Meanwhile, Expand continues to scale horizontally due to being able to manage the multiple client threads more efficiently with minimal overhead. The Xbench is able to manage each of these environments separately, as the cloud for Cockroach and the Expand SkySQL environment are totally different. But Xbench is able to manage them as separate clusters and automate testing to each of them. And so for this last example, I'd like to showcase the ability to test new features. Earlier, I believe the X project was announced in OpenWorks, and we're calling it Exgress here, is basically using the Postgres foreign data wrapper to allow processing Postgres queries by Expand. We're going to run some performance tests, and we have some data here automated using Xbench. We're running this time as a TPCC workload, which uses a type of distribution that spans all the warehouses in the data set. And since this database is larger than the system memory available, there's going to be a lot more disk I/O. This means we're going to see a lot of the limitation come sooner, as you can see with Postgres, just a default vanilla installation. Meanwhile, the Exgress comparison continues to scale out, which is expected as Expand is able to handle more concurrent threads. Now, this solves scale limitations and improves resilience, but being able to implement it into Xbench was a bit of a challenge because we needed to understand what Exgress looks like. And so this is how we implemented Exgress into Xbench. We looked at it and considered it both a proxy and a backend. In the definition here, in the implementation YAML, we're saying that the proxy is using Exgress and the backend is Expand. But because Exgress uses Postgres backend as well, we actually inherit the existing Postgres backend implementation that we had already and combined it with this proxy function. This allows us to maintain the same cluster connectivity. The topology will look very similar to the standard Expand installation, as it should be because we're still using Expand in the backend. So this is another example of just being able to extend the capabilities of Xbench. Okay, well, that's all I have for you guys today. I want to thank you for attending this presentation. A couple points here. Xbench is on its way to becoming open source. So keep an eye out on this GitHub repo, Xbench community, as we'll begin committing into it and adding READMEs and documentation. That way you can try this all out yourself. I'd also recommend reading this full article on the Cockroach and SkySQL comparison we made and that I referenced earlier in the example. Lastly, reach out to MariaDB if you'd like any more information on any of our products. And thanks again, and I hope you enjoy the rest of OpenWorks.